Farook received technical licentiate and PhD degrees from Lund University in Sweden and has a Bachelor of Engineering and Master of Engineering from Bangladesh University of Engineering and Technology in Dhaka in electrical and electronics engineering. Farook has extensive experience and expertise as an academic, as well as in collaborating across multiple disciplines. He was a faculty member in the Department of Information Engineering in the School of Electrical and Electronic Engineering, Nanyang Technological University in Singapore before he moved to Canada with his family. He has been affiliated with various universities/institutions in Canada as a research faculty, as well as visiting scientist and academic advisor. His research interests include signal and image processing, pattern recognition and machine learning, intelligent systems, speech/audio processing, bioacoustics, big data, computer vision, and data hiding. He has published over 130 research articles in refereed journals, conference proceedings, and book chapters. Thank you for joining us today, Farook. You need to unmute.
But, okay, that's fine. Can you see my slides?
No, you
no, not yet, share? Because I need to, sorry for this disruption. I need to, share my slides, which is, yeah, that's just a moment. Yeah. Is it all right now? Can you see?
Yep, perfect.
Okay, thank you so much. Good morning to all of you. And thank you so much, Jesper and Romina, for inviting me for this talk. Can you hear me clearly? Okay. So this is the outline of my talk. We actually investigate the plain fin midshipman fish in this study, and it is proven to be a special species for studies of wild fish communication and fish behavior. As we know that this plain fin midshipman fish is a highly vocal fish. It is called found in Pacific, mainly in Pacific Northeast coast, and it is called a singing fish. It is very remarkable in terms of producing unique and varied sounds. So far, the harm sound, which has been well understood, well researched, which related to the associate with the reproduction. But the other important social calls which midshipmans produce are the grunt, growl, and groan. They are not, in comparison to harm sound, it's not well researched and well established. And another thing is that this is quite challenging problem because these sound are very identical and they are very spectrally, they are overlapped. So it is like a challenging problem. So that's why we are focusing on to study this three type of social calls produced by midshipman fish. For example, if growls are emitted as an agonistic response for the predators, so an increase in growls tells us that the high abundance of predators. So we mainly focus on designing an effective classification scheme in noisy hydrophone data using robust principal component analysis and multi-resolution acoustic features. So PCA, we know that principal component analysis, which actually used singular value decomposition to find the lower rank matrix of the data. While robust PCA, in fact, they can identify the low rank representation or low rank matrix, as well as random noise and a set of outliers, which can be done iteratively by calculating the SVD, applying the threshold on the singular values and error for each iteration. So RPCA or robust PCA actually plays a significant role to tackle this challenging problem while concerning with big data by minimizing the false alarm and also when the data are not normally distributed. So another interesting feature we newly imposed here to extract the acoustic features using multiple windows. So we have used both 1D and 2D windows for the same data. So this multiple window actually enlarge our feature set, and it can also handle the diversity of the ocean data by increasing the number of examples. So the proposed method, can be outlined in 2 steps. In the first step, we actually partition the raw hydrophone data. In the second stage, we design or construct the feature set. Then we apply the feature selection, and selected feature has been used to a multiclass SVM classifier to track the type of vocalizations. Here is the overall flowchart of the proposed scheme. So for pre-processing, we have considered some manual spectrogram analysis, which involved the manual annotation for the first 5 minutes of each hydrophone data, feed data for different dates, and type and length of feed data for each 5-minute segments are then determined using the Audacity by an expert. All extracted segments are then resampled and resized, followed by a n-sample Hamming window. So here is what I want to reiterate is that we introduce a new feature set, which is based on energy distribution in the time frequency plane, which can be represented by cochleogram of the input signal. We incorporate a number of cochleograms at different resolution to design our improved feature set, which will define as MRAF feature set, multi-resolution acoustic feature set. The cochleogram with low resolution captures the local information, whereas the cochleogram with high resolution captures the local information, whereas the cochleogram with low resolution captures the contextual information at different scales. For example, in order to calculate the cochleogram, we can consider that the input signal will be passed through a gamma tone filter bank, and for output of each filter bank can be divided into 20 millisecond frames with 50% overlap, that is 10 millisecond frame shift. Then the cochleogram can be obtained by calculating the energy of each time frame at each frequency band. So here are the steps to compute our feature matrix or feature set. If given an ocean data, we first compute a first 64-channel cochleogram, followed by taking the log operation for each time frequency point. Similarly, we calculate the second cochleogram, CB2, which is using a longer window size, which is 200 millisecond, with a frame shift of 10 millisecond. The third cochleogram, CB3, is derived by averaging CB1 using a 2-dimensional window of size 5 by 5, so that which include 5 frequency channels and 5 time frames for a given time frequency point. If there is a problem with the size, then we can use zero padding. The fourth cochleogram, CB4, we computed similarly with CB3, except that we increase the size of the 2D window, which is 11 by 11 size has been used. Then we concatenate all the 4 cochleograms as CB1 to CB4 to generate our feature matrix, which can incorporate both local information as well as contextual information. And then we integrate it along the time frame to obtain a set of feature vector, which is size will be 256 by 1. We have considered feature selection motivated by the idea of matrix decomposition to decompose the feature matrix into low rank matrix and a sparse matrix based on alternating direction method. And this leads us to a robust principal component analysis based on convex optimization. The robust PCA is basically a matrix decomposition problem when it assumes that the input feature matrix can be decomposed as a low rank matrix and a sparse matrix. And recovery of this low rank matrix L and S matrix can be accomplished by the following convex programming problem, where you can see this convex function, which can be a weighted sum of the 2 norms. That means one is a nuclear norm, another was L1 norm, where is lambda is a positive regularization parameter. And for the multiclass, for the classification, we have applied multiclass SVM classifier. In general, the multiclass SVM classifier can solve the D-class classification problem by constructing decision function which is in this form. So basic idea is multi-class classification is that you have a data, you convert it with the kernel in the feature space, then you find that optimal hyperplane. This optimal hyperplane for each class C, which is, we have a D class here, D number of classes here, can be defined or represented by the weights W, C and bias term BC, so that the hyperplane, the margin between this hyperplane will be maximized. So we have to find out optimal weights of WC and BC. There are different models which you can consider for multi-class SVM classifier, but here we have considered CS multi-class SVM classifier, which is based on Kramer and Singer model. We consider all the data in one optimization formulation, and it can provide us a fast convergence and high accuracy. So data has been collected, fish data has been collected passively of a private dock in the east coast of Quadra Island, the state of Georgia and British Columbia, using a hydrophone, which is secured in the seafloor at a between distance 1.5 meter to 7.5 meter. We have considered here 3 dates in the June to this 2012 data, and 3 dates are 7th, 15th, and 22nd June, and all this data has fish calls, grants, growls, and grown. So we have considered 3 continuous 24-hour data to adapt our evaluate performance. Here is the number of fish vocalization segments we have used for our performance evaluation. Okay, sorry. Here I show you a typical samples for grant, growl, and groan calls. And you can see that the first one is grant, and then second middle one is the growl, and this is the groan. And you can see the spectrogram is shown here. The x-axis is the time axis, y-axis is the frequency, and you can see that they are actually signals is within a band of 100 hertz. And they're pretty similar in terms of frequency or bandwidth. Here is the examples of cochleograms we have used for feature matrix. And we can see that x-axis is the time frame and y-axis is the number of channels. So the first one is representing the segments for grant. This second middle one is the growl, and the third one is for groan calls. For the classification purpose, we have actually used our real data, fish data, which we have run 100 times. Different runs have been selected based on the feature set, which has been selected randomly. And 2/3 of the features data has been used for training, and 1/3 of the data used for testing. And before using this, we normalize the feature set to zero mean and unit null. And also we have selected 2 parameters for our multi-class SVM classifier. C is the regulation parameter, and here gamma is the bandwidth parameter. So we actually consider the default parameter C equals to 10 and gamma equals to 2 for our, and the kernel we use a radial basis function kernel, the Gaussian kernel. So we have considered the following calculation of classification accuracy and calculation of sensitivity and specificity for our performance evaluation. Here is the result I have shown you based on our 24-hour fish data for different date at different feature size. M is the feature matrix, feature size. Feature size is 64, 128, 192, and 256. Where we can see that for June 15th, the result for accuracy result is higher than 90% compared to the other 2 data set, which has been recorded on June 7 and June 22nd. And this main reason is the signal to noise ratio. As we see, that signal to noise ratio, average signal to noise ratio is higher, about 7 dB for June 15th data compared to the other 2 data, which is lower, 5 dB and 3.5 dB. Here I show you the confusion matrix, which show the sensitivity and specificity. Here you can see that the sensitivity and specificity for the grant calls are much higher than the other two calls, like grown and grown calls. And that is expected because the SNR for the grant calls we have found is higher, and also the number of samples for the grant calls is higher, and lower specificity and sensitivity is mainly due to the small number of data samples, vocalizations, as well as low SNR, which happened for data which recorded on June 7th and June 22nd. Then we have introduced our feature selection module based on robust PCA. You can see that after deploying, incorporating the feature selection on the feature matrix, we have seen that the results for June 7 and June 22nd especially are improved. And you can see that the improvement is more prominent for June 7 and June 22nd results when the SNR is low. So it is very interesting and important that when our SNR is low, then we can certainly employ our feature selection method to improve the results. We have actually compared the result with a similar method, and we compare one method. We found this method, which gives us the best result among other methods. There are not many methods available. So we have found that even if this method is performance well for this data set, but for our data, the result is not convincing. The result is quite low and poor in the sense that the classification accuracy we received is less than 50%. And also this can be happen because mainly due to the susceptibility of the method to noise and distortions. In this particular method, they have used temporal features which based on zero crossings and local maxima, so which is naturally quite susceptible to the noise and distortions. We have compared our yes. We have compared our result with MFCC, and we have found this, the parameters have been used for MFCC, and we have found that MFCC, for the MFCC parameters, the results are not as good as we obtained using our feature set. So this is the confusion matrix we obtained for the MFCC features. So as a conclusion, I want to say that this paper introduced a new method for long-term monitoring of fish sound using noisy ocean data. The framework is quite effective in classifying this type of three types of fish sounds, which is challenging due to its identical behavior and overlapping spectral content. And experimenters show that our performance is better than MFCC features. The proposed method actually constructed based on local and contextual information. And we also have a feature selection based on robust PCA, which can improve further our results. So we actually acknowledge the collaborator of this, co-worker of this project, Dr. Sharika Kuli-Suzuki and Dr. Feng Jing, for their substantial contribution for this project. Thank you so much for your kind attention, time and kind attention, and any questions, I'm happy to answer it. Thank you.
Thank you so much, Farook. I'm not seeing any immediate questions in the chat. If anybody wants to throw one out quickly, we hardly have time, and then we will move on to Debbie.
Okay.
And there'll also be time in the breakout room in just a little bit. Oh, sure. Yeah, somebody had asked as you were going through for an explanation of what a Cochlear Grand was. There was one provided, but if you wanted to fill any of that in.
A Cochlear Grand is that a kind of, it is actually based on auditory filter bank. Cochlear Grand is kind of auditory filter bank. So it can actually give you the auditory perceptual features. So basically what it is based on a gamma tone filter bank. The gamma tone filter bank is a perceptual filter or auditory filter. So you have input signal, you send it pass it to a gamma tone filter bank, and gamma tone filter bank has 26 critical band, and then for each output of this gamma tone filter bank, we apply a small segments, and then you calculate and then shift the glide the small segments and calculate the energy, and then you can get the output of the energy at each time point, at each time frame, each time frequency band. So this is a kind of time frequency representation based on auditory filters or gamma tone filters.
Okay, great.